Hello again, everybody. This is our video solution to problem 4 from Quiz 6, Fall 2023, Math 307, Linear Algebra at Cal State Fullerton. All right, let's see what we got here. It says, I asked the class to explain the connection between eigenvectors and one-dimensional invariant subspaces. Clever Carl writes, Clever Carl's back. He says, let T be an operator on V. Okay, we can do that. We call T invariant. Oh, no. Oh, that doesn't sound good. Oh, boy. We call T invariant if TV is an element of V for all V in V. Oh, wow. Okay. Since TV is in V, there exists a lambda such that TV equals lambda. Oh, this is painful. The vector V is an eigenvector. Yeah, well, there are words in this, and those words are related to words that are related to this topic, and that's about as good as we can say for Clever Carl's description. So let's try to help Carl out here. We want to describe the connection between eigenvectors and one-dimensional invariant subspaces. So let's quickly remind ourselves what these things are. So eigenvectors are going to be some non-zero vector V such that TV is equal to lambda V for some lambda. All right, so some lambda and F. All right, and now what is this one-dimensional invariant subspace bit? Well, one-dimensional just means it's dimension 1, and it's a subspace. We got that there. What is this invariant bit? Well, the invariant is referring to what happens when you apply T to that subspace. And so the idea here is you have some subspace, U of V. Of course, the dimension of U needs to be 1. And then if I apply T to U, I should get a subspace of U. Right? Of course, being one-dimensional, there's not too many options, it turns out. All right, so let's try to rewrite what Carl is doing here. Let's see. Let T be an operator on V. You know what? Carl did okay there, right? We're allowed to look at operators on V. It says we call T invariant. All right, so how about we're going to keep this bit, but now starting here at 1, we're going to say, well, what do we need? We need actually a subspace. So a subspace, let's call it U. U of V is T invariant if the T image of U is contained in U. All right, so if you like, T of any element in U is an element of U. All right, now, what if we had a one-dimensional invariant subspace? So if the dimension of U is equal to 1, well, then we know that U has a basis with just one element in it. So then there exists a basis of the form, well, we just have this one element. We'll call it U. Now, because it's a basis, we know that it's linearly independent, so U can't be 0. All right? For some U in U not equal to 0. All right, so what happens if I apply T to U? So we have TU. Well, we know that T of U, big U, right? Like if I apply T to the entire space U, I end up back in U. So in particular, if I apply T to little u, the image is again in U. But U, we just said, is spanned by this one element U. But the span of just one element just means it's a multiple of the element. All right, so thus, there exists some lambda in F such that TU is equal to lambda U, right? TU has to be a multiple of U because it's in the span of U. Of course, once you know that TU is equal to lambda U, well, now if you have any multiple of U, right? So this implies if you take any multiple of U, say some alpha U, this will be alpha TU, which will be alpha times lambda U. which will be the same as lambda times alpha u. So in fact, all of the non-zero elements in U are eigenvectors, and they all have the same eigenvalue, lambda. So thus, every element of U, other than 0, right? 0 is never an eigenvector. So every element of U not 0 is an eigenvector with eigenvalue lambda. Okay, where this lambda, remember, this came, right, by asking, okay, what is T of U? Well, it's got to be some lambda U. So this is the eigenvalue for everything in U. All right, so this would be a description of the connection between eigenvectors and one-dimensional invariant subspaces. If you have a one-dimensional invariant subspace, every non-zero element is an eigenvector, and there is a common eigenvalue given by just, well, apply T to anything, whatever the eigenvalue is, that'll work for all of the non-zero elements. All right, everybody, we will see you next time.